All right, welcome to Unit 5 on sampling distributions. This video is going to focus on topic 5.5, sampling distributions for a sample proportion. All right, over the last couple of lessons, we've talked about some big ideas. So one big idea is that one sample statistic by itself really does not tell us a whole lot about the population from which it was taken. What we need to do is compare the one sample statistic to all other sample statistics from samples of the same size from the same population, which is of course a sampling distribution. Once we have a picture of what all possible sample statistics could look like, then it becomes really easy for us to understand how our sample fits in amongst those other sample statistics. So that's really where we're going with this, is that, it's all about trying to find the truth. And, if all I do is I take one sample proportion and I get something like 31%, that doesn't tell me anything about the true population. I need to take a look at a bunch of samples and a bunch of p-hats from every sample. Then I can understand what the truth of the population is. But there's one big question that I'm hoping maybe you're thinking, one big question that should arise. If a sampling distribution contain a statistic for all possible samples, how the heck can we build one? There's millions upon millions of samples out there, especially with large populations. How the heck are we supposed to look at every single sample? It's impossible. Well, it's actually really easy to do. And the crazy thing is, we don't even have to look at any samples to do so. So let's pick right into it. There are three parts to all sampling distributions. The first part is the center. The center is literally the mean of all the possible sample proportions that exist. As long as the samples are drawn random to avoid being biased, then the center is the true population proportion. Remember, a sampling distribution it's filled with p-hats. Well, some are going to be higher, some are going to be lower. But what happens is you'll start to see a pattern. You'll start to see all those p-hats kind of like filling up, kind of centering around one center hump. And that, my friends, is the true P. So please note two things on this slide. One is the symbol. The mean of all the p-hats is equal to the truth, smack dab in the center. But there's one important condition that I emphasize in red here, is that the center is only going to be the truth if your samples are random to avoid being biased. All right, part two. The second part to a sampling distribution is the spread. Understanding that some samples are naturally going to be higher, some samples are naturally going to be lower. So all sample proportions are obviously going to vary a little bit. Now we can actually measure this variation with the standard deviation. Now in the past, we were just kind of estimating what the standard deviation is, but now we have a formula to find it. A formula to find the standard deviation of a sampling distribution is amazingly easy. You just take the square root of the true P times 1 minus the true P divided by your sample size. And this will give you, again, notice the symbol here, the standard deviation of all the p-hats. Now, it's a really easy formula. It's very simple to use. All you need to know is the truth. And you might say, well, how am I supposed to find the truth? Go back to part one. The center is the truth, so you better know the truth. Now, there's a huge condition here as well. The samples all have to be independent of each other. So if I take a sample out, I got to put it back, mix it up, take out another sample. Well, let's talk about that for a second. For the variation to be calculatable with the formula that I just gave you, it does require that samples are independent of each other. But in the real world, we just cannot sample like that. We cannot take out 75 babies, for example, replace them back, mix them up, pick out 75 again. It's really just not feasible. So we oftentimes, when we sample, we do so without replacement, which sounds really bad because we talked about when you sample without replacement, you're affecting the probabilities, which is bad when it comes to standard deviation. But this is super important. It's actually okay, as long as we meet this rule. As long as our sample size is under 10% of the population size, we're okay. Listen, technically, if we sample without replacement, our samples will not be independent of each other. But as long as our sample size isn't too big, the slight difference is negligible, which means it's not big enough for us to worry about. So the idea here is that we don't want our samples to be too big, and the rule is that as long as your sample is under 10% of the population, you're A-okay. Now, to understand this, think about sampling Skittles. If I have a very small bag of Skittles, maybe 20 total Skittles, if I take out 5, put them aside, take out another 5, put them aside, take out another 5, put them aside, the problem is, very quickly I'm going to run out of Skittles. And every time I take out 5, I am literally affecting the proportion that is left in that bag. But again, that's because I'm taking out a lot. 5 out of 20 is 25%. So I'm literally taking out 25% of the Skittles every time, which is a big chunk. But now let's go to a large batch of Skittles at the factory. I'm talking hundreds of thousands of Skittles. If you take out 5, keep them out. Take out another 5, keep them out. Now, technically, are you changing what's left? Yes. But that change, we say, is very negligible. It's not a big change that we worry about. And think about that. If you take out 5 out of 100,000 Skittles, you're only taking out around well less than 1%. So you're not taking out enough to really affect anything. And that's where we get this idea. Remember, this all stems from we need independence. We need to sample with replacement, but it's just not feasible. So the rule says as long as your sample size is under 10% of the population size, it's okay if you don't put them back. You'll be okay. There might be a small difference, but it's a negligible one. But wait, let's talk about one more thing since we're on the topic of sample size. Repeat after me. Bigger samples vary less. Bigger samples vary less. Bigger samples vary less. The law of large numbers. Take out bigger samples, you'll get closer to the truth. So guys, sample size matters. The standard deviation of a sample proportions describes how far sample proportions are from the mean. Right? That's what this formula tells us. How far we expect other sample proportions to be from the truth. But bigger samples will always produce less variability, hence sample proportions that are closer to the mean. If you don't believe me, look at this example. Let's suppose that 30% of all Skittles are red. So the center of a distribution would be that truth, 0.3. And the formula for the standard deviation. Now let's look at standard deviation for a sample size of 50 and a sample size of 200. So on top, again, we got a giant square root. On top goes the true P, 0.3, 1 minus that, 0.7. That doesn't change. But the bottom is the sample size. And when you divide by 50, as opposed to dividing by 200, you get a much smaller standard deviation. So with only 50 Skittles, we would expect, somewhere around a 6% swing, 6% higher, 6% lower, which is a pretty big variability. But with only 200, with 200 in our sample, we would only expect about a 3% swing, 3% too high, 3% too low, which is much smaller. In fact, if you actually look at these numbers, 0.0324 is exactly half of 0.0648. And to achieve half a standard deviation, you actually have to times your sample size by 4. Now, why do you times it by 4? Because of the square root. When you're in a square root, the square root of 4 is 2. So when we times the 50 by 4 to get 200, since that 4 is in a square root, it's really a 2, which is why it cuts our standard deviation in half. So it's really important to understand that bigger samples vary less. Hopefully that little example proves it. All right, one more part. The third part to a sampling distribution is the shape. Now the shape of a sampling distribution for a sample proportion will be normal. This is fantastic news. We love the normal model. But why is it normal? Well, to be honest, The central limit theorem that tells us sampling distributions will be normal only applies when you're working with means. When you're working with proportions, it honestly does not apply. But we have a very simple rule. As long as your sample size has 10 or more successes and 10 or more failures, then we say that the sample size is big enough to be normal. Now, what the heck do I mean by 10 or more successes, 10 or more failures? So let's go with our 200 Skittles. We know that 30% are red. What that means is in a sample, we need to expect 10 or more successfully red Skittles and 10 or more successfully not red Skittles. So that's easy to figure out, right? If we take 200, times it by 30%, 200 times 30% says that you should expect 60 red Skittles. Hey, that's more than 10. And if you take 200 and times it by 70%, you get 140, which, hey, that's more than 140 non-red Skittles. So as long as any one sample is expected to have 10 or more successes and 10 or more failures. Remember, successes is just defined as P, and failures is the opposite of P. As long as you have 10 or more successes, 10 or more failures, you will be big enough to be normal. All right, so in summary, we want to create a sampling distribution that shows us what all possible sample proportions look like. All we need to know is three things. The mean is the center, the truth. The mean of all the p-hats is the true p, provided that our samples are random. The standard deviation to show the spread is the square root of that true p times 1 minus the p divided by n. Again, provided that we're independents. But remember, we typically don't sample with replacement, so we do have to check that our sample size is under 10% of the population so that we can assume independence. And thirdly, the shape is going to be normal. But we only are going to get that normal shape as long as our samples have 10 or more successes and 10 or more failures expected. Now, with those three things, we could build a sampling distribution without taking a single sample. This is crazy. It's crazy. Like, you don't even need to take any samples to know what they're all going to look like. It's absolutely insane, but it's true. All you need to know is the true proportion and, of course, the sample size. If you look back over here, everything on this page requires the true p and the sample size. And again, the true p is used here again. And with those two things, you could build a sampling distribution. Now, since sampling distributions have a mean, they have a standard deviation, and they're normal, we could calculate probabilities. We could calculate probabilities of any interval. We could calculate probabilities above. We could calculate probabilities below. We could calculate probabilities in between. We could even determine what would determine a significantly high or a significantly low sample. Now, just keep remembering one thing. The only thing the normal model cannot do is calculate an exact values probability. It can do intervals more, less, cannot do an exact value. All right, guys, that's it. I just taught you everything you need. Let's look at some examples. All right, suppose that 35% of college students in the U.S. attend a college that is within 50 miles of their home. So 35% of kids that go to college across the country go to a college within 50 miles of their home. Describe a sampling distribution if 1,500 college students were sampled. So we want to say, what would all possible samples look like? Oh, by the way, we haven't even looked at any, but we could do it. Now, when I tell you to describe, you need to remember that means three things. Find the center, the mean, spread, the standard deviation, and the shape. We know it's going to be normal. All right, so here I go. Let's talk about the center first. All right, the mean of all the p-hats is going to be centered at the truth. If the truth is 35%, yes, some might be higher, some might be lower, but we should start seeing the large majority gravitate towards that center of 35%. But we do have to ensure that the samples were all selected randomly to avoid bias. 2. The standard deviation of our sampling distribution can be found quite easily using the formula square root. The true proportion of kids that live within 50 miles is 0.35. The opposite of that is 0.65 divided by our sample size. Because our sample size is really big, notice that this produces a very, very small standard deviation of right around 1%. That's 1% high or 1% low. That's a very small standard deviation. But, wait a minute. We could only calculate standard deviation if we have independence. Technically, we don't because we're not sampling with replacement. But because it's safe to assume that 1,500 college kids is under 10% of all college kids. Guys, come on. There's millions of college kids in this country. 1,500 of them is definitely under 10% of all of them. So basically, taking out 1,500 isn't going to make that big of a difference. So I can assume independence is true. Finally, a beautiful shape is going to be normal. But remember, the shape is only going to be normal if I could expect 10 or more successes and failures. So you actually need to show the work for this. So I took 1,500 times P, and that's about 525 kids that are supposed to live near 50 miles from their home, more than 10. And then I'm going to take 1,500, that's N, times the opposite of P, 1 minus P, 0.65, and I get 975. That means 975 kids do not live within 50 miles of their home. As long as both of those numbers are 10 or bigger, the normal model is safe to be used. If either one of those comes back under 10, honestly, guys, you shouldn't draw the normal model. All right, let's put all three together. Center 0.35, standard deviation 0.0123, shape normal. I even labeled it. I put the center in the middle. I went up 1, I went up 2, I went up 3 standard deviations. Down 1, down 2, down 3 standard deviations. Guys, think about how powerful this is. I just made a picture of what all possible sample proportions will look like. And I didn't even take a single sample. All right, let's answer some probability questions. Now that we know the mean, standard deviation, and the shape, we could use it to answer all different questions about probability. Note, anytime you find those three things, you have to check each condition that goes with them. I emphasize those in red. Please make sure you don't forget to do that. All right, here's a question. What is the probability that a sample of 1,500 college students reveals 37% or more live within 50 miles of home? So I want to find the probability that a sample is more than 37%. Well, all I got to do is calculate a z-score. Take 37%, subtract the mean, 0.35, divide by the standard deviation, get a z-score, 0.37 minus 0.35, divided by 0.0123, 1.6260. Which means I need to find the probability that a z-score is greater than 1.6260. Again, that's hovering right around here. I need to use normal CDF on my calculator to do so. I'm going to go from 1.6260 to infinity, mean of 0, standard deviation of 1. 1.6260 to 99. Remember, on my calculator, I'm going to type infinity is 99. 0.0520. There's about a 5% chance that a sample of 1,500 kids comes back 37 or more. Please note that the normal model does not distinguish the difference between greater than or greater than or equal to. It doesn't matter. All right, find the probability that a random sample of 1,500 students will give a result within 2 percentage points. Now, remember, within 2 percentage points means 2%, within means up or down. So plus or minus. So the center is 35%. So we're looking from 34% to 36%. Sorry, 34% is not where I drew it. I'm so sorry. We're looking for about 34% to 36%. Remember, oh my goodness. I need to just stop right now. I'm very, very sorry. Hopefully somebody at home is wondering what the heck I'm talking about. within 2 percentage points. That's 33% to 37%. 0.33 to 0.37. So I need to find the probability the sample is in between those two numbers. So I got to find the z-score. Now, luckily, I already found the z-score for 37%. I could just reuse it. That z-score was 1.6260. Now I got to find the z-score for 0.33 minus 0.35 divided by 0.0123. And lo and behold, it's the exact same z-score, but negative. That's because of symmetry, guys. If you go up 2% and then down 2%, you should be getting the same z-score, one positive, one negative. So I'm going to look to find the probability that a z-score is between negative 1.6260 and positive 1.6260, which I'm going to use normal CDF to find. I'm going to go from negative 1.6260 to positive 1.6260, mean 1, standard deviation, mean 0, standard deviation 1. Pretty easy to do this on a calculator. And we get 0.8961. 89.61% of samples, not kids, remember this is showing samples, will be in between here and here, about negative 1.62 to positive 1.62. Last question. If a sample of 1,500 college students from Ohio came back that 40% live within 50 miles of home, would you be surprised? Well, remember, what does being surprised mean to us? That means it's significant. That means it's very unlikely to happen, which is under a 1% probability. So I need to find the probability that a sample comes back at 40% or more. Now, why am I doing or more? Remember, this is a p-value. 40% is on the high side. So, or more extreme, or more significant would be any higher than that. So, I got to find the z-score for 40%, which I hope you could already tell is off the charts. So, it's going to be taking the difference, 0.4 minus 0.35, divided by 0.0123, and you get a z-score of 4.0650, which, like I said, is off the charts, unbelievably high. To find the probability of that, I'm going to go ahead and do normal CDF. Going towards infinity, mean 1, oh my gosh, always mess it up, mean 0, standard deviation 1, 4.0650. Remember, when you use your calculator, you're going above to 99. We get a very low number, 0.00024. So would I be surprised if a sample came back 40% or more? Please do not say 40% exactly. Normal model cannot calculate that. But the probability that a sample comes back 40% or more is extremely, extremely unlikely. So yes, I would be surprised because it would have a probability under 1% of occurring. The probability of a sample coming back 40% or more would be under 1%, which tells me that it's very surprising. So notice that what I just did right there was I explained. Got to explain that. All right. So what would it mean? If a sample did come back at 40%, what would it mean? Well, it could mean a couple things. One thing it could mean is that my sample was weird. Maybe the sample I looked at was kids from Pennsylvania. And that would tell me that obviously in Pennsylvania, kids like to live closer to home. A larger proportion of kids in Pennsylvania want to live closer to home, within 50 miles. Something about being grown up in Pennsylvania causes kids to love their parents more and want to be closer to them. Maybe that's what it is. So maybe I just had a sample from Pennsylvania, and for the United States it's 35%, but Pennsylvania, it's higher, showing Pennsylvania students love their parents more. I don't know. Another possibility is if my sample was not from Pennsylvania, it was just a random sample, then maybe this number, 35%, was true 10 years ago. Maybe 10 years ago, 35% of kids went to a college within 50 miles of their house. But now, in 2020, maybe that proportion has risen. So maybe we thought it was 35%, but now the truth is that it's actually higher. Because if I picked up this whole normal model and I moved it higher, then, sorry for the terrible drawing there, then all of a sudden, 40% would not be weird. All right, guys. I don't know what you're thinking right now, but I hope you're thinking, dang, this is pretty darn easy. So good luck. See you in the future.